Hi everyone, you're watching Python tutorials on my YouTube channel Python for Microscopists. Well, this is not just for microscopists, this is for anyone who is interested in using Python for image and data analysis. Now in the last tutorial, we looked at how we don't need a lot of data for traditional machine learning. In fact, we used convolutional neural network and removed the neural part, just took the convolutional filters for feature generation and used random forest or support vector machines for classification. So for that, you don't need a lot of data. So if you plan on applying a model on new data that's coming up, then you may as well train on the new data because it doesn't take a lot of data for traditional machine learning. But if you are doing deep neural networks, and you're training it for a reason, right? I mean, you want to deploy it somewhere so you can kind of use it in a production mode. Otherwise, what's the point in labeling thousands of images or a lot of data for deep neural networks? So if you do that, now what happens when new data comes in? Does the new data look like the old data? If not, at what point do you have to think about retraining it, and what are the indicators, if any? We can use statistical means. For example, if you have done any engineering field, you probably are trained to use student t-test. Yeah, are these two data sets similar? So this is your student t-test, right? It actually looks at the mean, but that's not a great tool to compare data sets, especially the data sets like these, because it assumes that the distribution is normal, like Gaussian, and it also only works when comparing the mean. If your variance changes, then it fails. So there is another statistic called KS statistic that you can use, and I'll show you how to use it. Just 2 lines of code. It actually works okay for non-image based data, but for image type of data, that also fails. That doesn't work. So I will show you another trick in terms of comparing two images. In fact, we'll use random forest for that trick or support vector machine. So please stay tuned and watch that. But the primary indication is how the images actually look. So let me jump in. And I created, like you probably recognize, most of you, especially if you worked with this type of data, you recognize this data set. Again, go ahead and Google search for mitochondria deep learning dataset, and you'll find this, and you can download it. Okay, so here you can see on the left hand side I have an original image, and on the right hand side I have image collected on a different microscope. Okay, so I use the left hand side image to train an algorithm, but does it work on images on the right hand side? This one looks low contrast, and also the brightness seems to be on the lighter side. So this kind of looks like this image, but it's not exactly. Maybe some pre-processing helps, but is it time to retrain? Well, the best thing to do is take the old model, apply, and see if it's working. So for example, if you see something like this, wow, that's amazing, it's working, but that's not the segmentation result. That's the ground truth, actually. Yeah, the segmentation result is this, extremely horrible. Okay, so in this case, I know that I have to retrain this, or maybe because my model was working fine on original images, right? So I know I have to retrain this. Now, if you cannot check this, if you cannot check this on the new data that's coming in, I'll show you a couple of ways of actually, analyzing your data so you can figure out whether you need to retrain or not. Again, this applies to any data, not just image, but especially for images, you need to be extra careful. So again, I promise this not to be a very long video, so please stay with me here. Okay, so let's actually read my training images and also the one that's low contrast. Okay, the original images and low contrast. All I'm trying to do is compare these two. And at the end of this, I'll also tell you what is the best way to retrain when it comes down to retrain. Again, it's just a quick little statement, but let's wait until the end. So here again, not going to explain every line, but all I'm trying to do is read these two. When I say individual image, this is actually a TIFF stack of 330 images, so it's not just one image. This 330 images, each image almost 1K by 1K. So I'm reading these two images and I'm normalizing them. And We'll see why normalization is important in a second, but if you look up here, so my input image is 330 images and 768 by 1024. 330 is showing up at the first because I'm using a TIFF file. Okay, and then it can directly read these multi-dimensional TIFF files. So that's why I'm using TIFF file library up here. Okay, so and I did normalize, so I called it set1 after normalization, before normalization image 1. And the reason I'm mentioning that is instead of working on all 330 images, let's just pick the top 10 images. Okay, so all I'm trying to do is pick the first 10 and somewhere in the middle 10 more images from each of this, so we can compare how things actually look when you compare them against, because the first 10 images are not same as the middle images, right? So there is a change in distribution, so this definitely helps. Okay, so now let's go ahead and plot, and while looking at the plot, I'll explain what we're looking at. I'm just plotting the histogram just to see how the data is distributed. So this can be any, it's not just image, it can be any data. So if you look up here, let's create a bit more room so you can see it. Okay, on the top left is my image 1. On the top right is my image 2, which is the low contrast image. So you can see that the mean here is around 130 or something, and here the mean is around 140, 150 or so, 145 to 150. So the mean has changed, and also look how broader this is compared to this. This is going only from 50 to 200. The data is ranging from 50 to 200. Here it's going from 100 to almost 200. So the data sets are slightly different, but does that mean I need to retrain? Well, first of all, I'm normalizing it. You remember, I'm normalizing it. Again, you can use any type of normalization. I'm not scaling, I'm normalizing. I'm doing min-max scaling, if you want to call it. So what that does is it puts the mean around 0 and then distributes it right around 0. So you can see now it's going from minus 0.5 to 0.6, and even here it's going from minus 0.5 to 0.6. The shape looks slightly different, but at least overall the structure looks very similar. Okay, so that shows you the importance of normalization in general, whether it is image data or non-image data, it doesn't matter. Okay, so it brings everything into one real scale. So that's very important. Now let's actually look at something called KS statistic. I say already that it's not a good metric, but it may be a good metric for non-image type of data. But KS metric, again, it's like student t-test. Again, I'm not gonna go into the KS metric science behind it, but right now all I'm trying to do is use this KS2 sample metric and compare the first image with the second one. Okay, so the first image is let's just take the first 10 images and then compare them against itself, so you know what we are talking about. Okay, so let's go ahead and run these two lines. Again, I'll share the code, so don't worry about it if you think it's going to be useful. And look down here. So the metric, the output is that the p-value equals to 1.0, which means if both data are very similar, then there is a higher probability. So the p here stands for the probability of both data sets being equal. Again, in statistics, there is called null hypothesis, and if this value, the p-value is less than 0.05 or 5%, okay, then we can almost definitively say that okay, these two data sets are different. Okay, well, in statistics you can never say anything different, anything definitively, but if the p-value is low, that means the data sets are different. If the p-value is high, the data sets are very similar. Our goal is to get this data sets to be very similar, right? I mean, these two data sets, then I can use my model. But the problem is, let's go ahead and print out these two. So these two are comparing the first 10 images in that same data set and images somewhere in the middle, and it's looking at this KS statistic. And if you look at that, the p-value equals to 0. That means it's telling me that these two data sets are different, but they're not. It's from the same, and I know it's working fine. That's why this is, and I also tested this on the normalized data. By the way, these two are unnormalized and this is normalized, and you'll see in a second, it still doesn't make sense. It's still reporting a value of 0. So again, I'm telling you that this exists, but then I'm telling you this is useless for images. Try this for non-image type of data. That's why I'm including it. Okay, now what do we do next? I think the best way to actually do this is you take all the images from this data set and then the low contrast data set, the two data sets, like the original one and the new one, mix them, and then fit it to a support vector machine or random forest, and then see if random forest can figure it out which image belongs to what. I hope this makes sense. If random forest can tell that, then your data sets are different. Because in an ideal world, if you mix this data, you shouldn't be able to tell where that data came from. Meaning your probability or random forest prediction rate should be 0.5, meaning 50% chance it comes from here or there. But if it is almost 100%, it's like, oh, I know where it comes from. So that's one way. I think this is a more robust way of telling that, hey, where the data is coming from. I know I'm talking a bit towards data and statistics, but if you want to be a data engineer, data scientist, machine learning engineer, in fact, I do interview people on a regular basis, especially data science roles. And one of the questions, I'm leaking the paper here, one of the questions I ask is, what is student t-test? How do you know two data sets are same? Okay, so be prepared to answer those questions. Otherwise, you're just copying code or writing code and you know nothing about the application or statistics, right? I mean, it's very important to learn tools that tell us how to handle data and how to interpret data. Okay, so now the second part I just talked about. So we have two data sets. We are merging them. Of course, we have to label them as the data set 1, data set 2. And then we merge them, we shuffle them, and then we randomly pick, and then let a random forest or support vector machines say, where is it coming from? If random forest is good at saying, oh, it came from 1 or 2, then our data sets are different. Statistically, they can tell the difference. If the probability equals to 0.5, meaning 50% chance it's coming from this or this, that means they're truly random. Let's see how to do that. Okay, so again, I'm just taking the set 1 of the first 10 and set 2 middle 10. So I have these two sets. I'm taking the first 10 images from the first set, and you can take the entire data set. But in this case, I have a very large data set, so I don't want to play with all that data. I have 330 images of 768 by 1024. That's tremendous amount of data. But I just need to sample a little bit. I don't need the entire thing, right? I mean, it's like telling whether the rice is cooked or not. You just need a couple of grains. You don't need to taste the entire thing. Okay, so let's just take the first 10 images and middle 10 images from set 2. So the idea here is we have two sets. So let's go ahead and do that. Okay, I'm saving that in a data frame because it's easy to handle data. So now you can see my set 1 data frame and set 2 data frame. I have tremendous amount of data still. So let's only subsample only 5,000 pixels of this entire thing, and I put a random state. I mean, these are randomly selecting 5,000. So if I look at my set 1 subset, you can see I only have 5,000 of these pixel values. And why are they some of these negative? Remember, we did min-max scalar, so some are negative, some are positive. Okay, so now right now these two are two different data sets. Now let's label them. So I'm going to add another column to subset 1 called data ID. Same thing for the second one, and I'm going to label the first one 1, second one 2. Okay, it only makes sense. I hope you're with me. Okay, so now if I open my set 2 data frame, for example, it says you have lots of it. Let's actually do it after the next step. Now let's do mix these two. Let's append set 2 to set 1. Okay, and reset the index. So let's go ahead and append and reset, meaning our index should now go from 0, 1, 2, 3. So let's look at set 1, set 2. If I can find it, I have too many parameters. Yeah, 10,000 right there. So I should have like first 5,000 with the ID of 1. Okay, the second 5,000 with an ID of 2 right there. So now I have one data frame with 5,000 pixels from set 1 and 5,000 pixels from set 2. Now let's shuffle it. Okay, so how do we do that? Again, in scikit-learn utilities, there is something called shuffle. So go ahead and shuffle it and reset the index. So you'll see how the outcome would look like. So let's look at shuffled. So we should have 10,000 of these. Now you see they're completely shuffled. So I have 2 here, a bunch of 1s here, 2s here, and so on. Now let's fit this to a random forest algorithm. Before doing that, obviously, what's our y? Our y is the ID of where it came from, and x is just the values, right? So let's go ahead and do that. And the next thing is, like we always do, split the data into train and test so we can test it after fitting it. Okay, so let's go ahead and do that. And you can try support vector machines, but let's just try random forest, because random forest for these type of applications would be even more accurate. So why not random forest? Okay, so let's go ahead and do random forest fitting, and then go ahead and predict on the test data set. And let's print out the accuracy score, and this is where the moment of truth. The accuracy is 0.69, so 69% it says it can detect. And let's actually look at the confusion matrix. And in fact, what I'm more interested in, I mean, this is the confusion matrix right there. I'm more interested in the bottom part right here, meaning which one is it doing better? That's not bad. I mean, on data 1, it says it's 73% accuracy in picking that. On data 2, it's 67% accuracy. Now the question is that different enough? In fact, let's come back here and say, change this to set 1. So now let's compare how random forest works if we take the first 10 images from this data set and the middle 10 images from the data set and shuffle them and see if the random forest can figure out the difference. What is the probability if we do that? Okay, so let's do this all the way, and let's just look at the values. And you see how the probability is 0.4995, like it's almost 0.5. That means it's random, 50-50. There's an equal chance of, which makes sense. That means my data set, even though I have 330 images, no matter where I pick, it seems to be doing good. Which means if I take some labels from that data set, train it, and then try to segment the entire data set or classify the entire data set, it does a great job. I know that for sure. Now the question is, how does it do on the other data sets, right? Data set 2. In this example, if we do this, it's telling me that the data set 2 is similar. I mean, you see right now, again, because there is a random seed, I get different results each time. It says accuracy on data set 1 is 57%. That's almost random. And accuracy on data 2 is 0.69, 70%. That's not random. It's actually a bit more confident this time. Yeah. So my data set 2 is slightly different. Now, where do you set a threshold? This is where experimenting with your model on a few of these images and getting an understanding on what that threshold value should be. If this accuracy goes up to 0.7 and you're still getting decent results with your initial model, you don't have to retrain. But then if you get very bad results, like this image that I showed you earlier, right? If you get these type of results and then you take these images and run through this and it comes up to be 0.8 or something, then you know that, well, my threshold should be at 0.7. I hope this makes sense. All we are trying to do is take your future images that you're coming, or the new images, and run through this code and see how well it matches your initial images that you have used for training. If it matches within certain agreeable limit, then you're okay, you don't need to retrain. If not, then you have to retrain. I know that's a very vague way of saying nothing beats seeing something like this and saying, okay, this is not working. But how many images can you see like this? How many times can you do this? If you can do this on a consistent way, that's fine, but if you cannot visualize your images regularly, but then if you can do this type of exercise, then this is please go ahead and continue with this. And let's actually look at let's run this one more time to see, because every time it's randomized, right? This is random forest. You can see that, okay, now this is 80% and 60%. Let's run this one more time and let's see how close or farther. Now it's 83%. All we are doing is trying to fit it, different ways. Now this is 83% confident. So this is getting up there. I'm not sure if I need to retrain or not. Let's just change this random state to 42 to see how that new split, I don't know, all of these random states, and then see how the new split actually affects. You have to do this 2-3 different ways and then see if that's actually affecting. Now by changing that, you see how my accuracy went up to 70%. That means the algorithm 70% of the time is able to distinguish between old data and new data, which is not good. We don't want it to distinguish. Okay, I hope we made that point clear now. Okay, now let's say you figured it out, you have to retrain for whatever reason. What is the best way? Well, the best way to retrain is, you probably already know, okay, you have, for example, code like this, and you do your model, and you train it, and you save that training. Do not forget to save it. Okay, so go ahead and save it, give it a name. In this case, I'm giving something, whatever that name is, and you can give a standard name, but it doesn't matter. You already save it. For example, here I'm saving the final trained model as malaria augmented model.h5. That's the final name I'm given. Okay, so this is the model I'm using over and over and over, and at some point I start getting new data that started to look slightly different than the previous one, because new data always looks different, whether it is Twitter analysis or some type of data analysis or some sort of image analysis. If it is images, it can be that your new images have more photo bleaching than the previous one. They're not, the contrast is different, the brightness is different. So there is no universal model that works on every image. Okay, so your model needs to be evolved as you get new data. So you need to retrain at some point depending on your data. So anyway, so I saved this model. Okay, now I need to load this model. Let's say a month from now, I get new data. So the way I do that is basically my new model is load model and then load the old model. With Keras, luckily, when you load the old model, all the weights and biases are already loaded. So when you're retraining it, it's basically you're providing the new starting point for weights and biases, and you're retraining it. Which means if you completely retrain on new data, it forgets old data. I think the term for this in deep learning is called catastrophic forgetting. Go Google search catastrophic forgetting. Read about it. So when you're retraining it, do not retrain only on the new data. Mix old and new data 50-50. If you have 1,000 images of old images and 1,000 new images, take them 50% from old and 50% from new, so it actually works equally well on both type of images. If you don't care about old images anymore, then that's fine. Then only use the new images. But try to mix them so the trained model is as generalized as possible. Okay, so that's pretty much it. Once you train this new model, then of course you go ahead and evaluate it, and using on the new data. Okay, so here you're loading the model, you're evaluating it, you're like, okay, I'm not happy with that, and then you go ahead and fit it again and you save the new model. That's it. But when you're training this again, go ahead and mix your images, old and new images, all into one bin, so it gets trained on this, and this is how it can generalize. Now please go ahead and Google search for how to train new models and how to train your old model using new data and all that, and please be careful when you're doing that. Always give unique file names. Never ever overwrite your old model names with the new one. So these are the mistakes I have done a few times, so I'm telling you not to make the same mistakes. Anyway, this video can be a bit on the dry side because we talked about numbers, we talked statistics, but these are very important if you're serious about getting a job in this field in future, whether you want to be a data scientist or machine learning engineer or even a researcher with skills such as these. You have to know, especially if you're a researcher, what is a t-test, what is KS test, and if get familiar with some of the statistical terms, because if you are interviewed by someone like me, you will definitely be asked these questions. So anyway, I hope you found this tutorial to be, again, useful, educational, and please go ahead and subscribe to this channel, and you'll learn a lot more information such as this. Thank you very much.